Hello and welcome to Autodesk Simulation TV. My name is Mike Fiedler, one of the Enterprise Support Specialists here at Autodesk. Today we're going to be looking at simulation in action, AutoCAD and simulation mechanical interoperability in the broader category of design and validation. So the description, what are we going to do today in greater detail? This demonstration is going to look at how we can utilize geometry that we create within the AutoCAD environment to produce analyses which will provide insight into the performance of our design. So beginning in AutoCAD Mechanical, we will then take the model that we have there, move it into the Autodesk Simulation Mechanical or Multiphysics environments. Anything we're going to do today can be done in mechanical or multiphysics. And then take a look at that. Once we apply some loads, some constraints, some properties to that model, do we want to change that design at all? Do we want to completely change it, make it look something completely different? Do we want to lengthen it? Do we want to shorten it? And so on. So what we're going to look at as far as objectives, how do we use AutoCAD line drawings to create line-based FEA elements or finite element analyses? Well, within simulation, mechanical, and multiphysics, there are numerous element types that you can use. Some of those are based on a simple line. Those include trusses, beams, springs, rigids. So just there we list 4 different elements that are all based on a line. Once we get into the simulation mechanical and multiphysics environment, you'll see that once I have that line geometry inside the analysis package, then I can give it specific properties that a truss needs, such as its cross-sectional area, or if I'm using a beam, I get more detailed and say it's a round section or rectangular section. If I were doing something like a spring, then all I need to do is tell it what's its axial stiffness or torsional stiffness. So all these different element types just beginning with a simple line. And then below that, how do we utilize AutoCAD areas or regions to create planar FEA elements? And again, you see that I've listed some different elements that are all planar elements. So if I begin with a enclosed region in AutoCAD, just envision a simple square, and I bring that into the simulation product, what I can do is mesh that region. Once I have that planar region meshed, then I can define it as 2D elements which say, what am I doing as far as translation in the Y direction or the Z direction? I can get into plate elements. Plate elements have a little more flexibility. Translations in X, Y, and Z as well as rotations. Shells, if I'm getting into mechanical event simulation, are very similar to plates. And then membrane for like fabric elements. Also, what are your loading and constraint considerations once you get into the simulation environment? What about analyses types? We're going to take a look at both a static and a mechanical event / nonlinear analysis in this presentation, and then ultimately how to review your results. Also down here I have a pretty long link. I will step out of the way for a minute so you can see that. I just note here, probably useful to review the documentation on importing CAD wireframes. I would say the simplest thing to do when you open up the simulation environment, if you go into the Getting Started and then access the wiki help, if you just type in the keyword in your search of AutoCAD, you'll get to this particular link here, and this will give you some greater detail as far as what we can import, working with those models and so forth. But we're going to cover a lot of it here today, but in addition it probably wouldn't hurt to take a look at what's available on the wiki. This next one we're going to do once we get it in the simulation, we're going to do a mechanical event simulation, and we're going to use some nonlinear materials. So this is a very simple sealing model or O-ring model that I made up here. So we have a pocket, and that of course is on one layer, so that becomes a part. And then I have an O-ring here or tube that I made on another layer, so that becomes part number 2. And then finally something to come down and close this model up. Layer number 3, or ultimately part number 3. So in AutoCAD, what we have are distinct areas. One of the nice things about simulation is it can realize, hey, here's an enclosed area. If you'd like me to, I can go ahead and put a mesh in that area for you. Here's another enclosed area defined by this outer boundary and an inner boundary, so let me put a mesh in there, and so on with the third part. So the program can automatically generate mesh within these enclosed areas. One of the conditions for this also, not only do they have to be enclosed, but they have to be unique part numbers, or in the case of AutoCAD, unique layer numbers. So in other words, if this was all layer 1 and this was all layer 1, it's not going to be able to put what becomes a part number 1 mesh here, skip across some void and then put a part 1 mesh there. It's going to have to be different part numbers in order for it to generate those distinct areas successfully. Okay, and then to explain what we're going to do with this model, in the last model we did, the bridge was a linear static stress. So we put some force on it in a static case, some infinite period of time. Time's not really a factor. What are our displacements? In this case, we're going to have motion. So we're going to push on this top part, and we're going to say it contacts this O-ring. The O-ring contacts the pocket here. And we're also going to have nonlinear materials. So we're going to define that O-ring as a rubber-like material. So we're going to use mechanical event simulation for motion plus the nonlinear materials. Let's go ahead and open up our simulation. Again, I'm just going to go File Open. We'll set the file of type that we're opening to a DWG. I'm going to choose my DWG, and before I actually open it, I'm going to press Options. Whoops. I chose Autodesk Inventor Fusion DWG. Wrong DWG. AutoCAD DWG. There we go. And when I go into Options, again, we are starting with a wireframe as opposed to a 3D model. In this case, the drawing is drawn in the XY plane, so I did note that. But we do want to transform it to the YZ plane. We're going to utilize 2D elements. And 2D elements in simulation have to be in the YZ plane. What it solves for translation-wise, what the model has degrees of freedom of, will be the Y direction translation, Z direction translation. So we do need to get it, if it wasn't already drawn in the YZ plane, we need to get it into that plane. That's what the transform is for. And I'm going to turn off the import lines, arcs, or splines as mesh lines. In this case, I just want to bring in the boundaries. I don't want to turn those lines into beam elements or truss elements. So I do not want to import them as mesh lines. So I'll turn that off. We'll say OK, and open up our seal drawing. As we do so, again, I'm going to choose the English inch unit system. And I'm going to change my analysis type from a static stress to a nonlinear mechanical event simulation with nonlinear. Okay, let me change to a right view, or YZ right. Notice the mini axis as soon as I move out of the way here. Y is now my horizontal, Z is my vertical direction, so it does need to be in the YZ plane. You can see, because I had my 3 different layers in AutoCAD, that I now have my 3 different parts within simulation, my 3 distinct regions. So how do I get a mesh on this geometry? Very simple thing to do. Towards the bottom, I have part 1 in the menu tree. Towards the bottom of any part, we have our element type, definition, material, surfaces. Right below that, you have a set of sketches that make up that part, because I did not import these as lines, so they become sketches. So I'm going to select the sketch there, select the second sketch group and my third. Once I have them selected, I'm going to right-click on any one of them. Again, all 3 are selected, and I'm just going to say Create 2D Mesh. Up comes the 2D Mesh dialog. There's option in here for you to change the parameters, so you can increase or decrease mesh density and specify a little bit about how it's meshing around angles and so forth. I'm going to accept the default, and we'll see what it looks like. Let's say Apply. Okay, and there's our mesh on it. For the purposes of the demonstration, we'll run with it. I'm going to turn off the construction vertices like I did before, and then also I have these black sketch lines. So we're going to turn those off as well. That would be on the View tab again. I'm going to deselect construction objects and construction vertices. Up to you, it's just a preference thing. I think it makes it look a little bit cleaner without it. Okay, so part number 1 is the little bracket that the O-ring is going to get squeezed into. Part number 3 is the part that's coming down and compressing my O-ring. Those 2 parts I'm just going to make nothing special. We're going to make them steel. First of all, let's define the element definition. Edit, element definition. And in this screen here, I'm going to leave them at isotropic as far as their material model is concerned. That's nothing fancy, same material properties in all direction. We're not going to specify a yield on them or anything fancy like that. Pretty much equivalent to the material model that was utilized in a linear static stress. What I do need to define, though, would be the thickness. So I'm going to give it a thickness of a 1/2 inch, 0.5 inch. I should mention here that what we're going to do is a planar model. So I'm saying I have a cross-section of something, it's a 1/2 inch thick. But you do have the option to do something that is plane strain. So if you've taken a section of something that's very long, where the out-of-plane stresses are generally negligible, something like a retaining wall or something like a dam across a river, that would be an example of a plane stress. Or a very long pipe under internal pressure, and you're just taking a cross-section of that away from the ends of it. Those would be plane strain. And then lastly, you have axisymmetric. So if you have a slice of something, and that something could be revolved about the z-axis, then that would be an axisymmetric model. So we're doing plane stress of something a 1/2 inch thick. Notice the element definitions get defined. And then the two materials for those two parts, we're going to make steel ASTM A36. All right. Now part 2 is going to be a little bit different. Let's go into the element definition for him. Because he is a rubber or hyperelastic type of material, I am going to choose a hyperelastic. And then there's a couple different material models there which describe those. I'm going to say it's Mooney-Rivlin. Again, plane stress, I'm going to give it the same thickness, 1/2 inch thick. So I'm telling this guy that he's going to be some sort of hyperelastic material. So I'm going to go in, I'm going to select the rubber material that's in the library here, and I'm going to make some edits to it. The rubber that's there is a, what do you want to say? It's pretty rigid, pretty stiff. So I'm just going to decrease the first and second constants that describe its behavior by a factor of 10. So 297 down to 29.7 and 172 to 17.2 to make it pretty soft. We'll say OK. All right, so next thing would be loads and constraints. For our constraints, I'm just going to fix the base of this model down here. The nice thing about importing models and generating this 2D mesh like this is each one of the boundary lines becomes a unique surface. So if I go point select, select surface, I can select that line right there, and I just want to constrain that. Add surface general constraints, we're going to make that fixed. Okay, and then on the top surface of the model here, we're going to add, and let me do this, select subentities of vertices. I'm going to select all the vertices across the top of that model, or that part, and we're going to add nodal prescribed displacements. So I'm telling these nodes that I want to displace them somewhere, and by a certain amount, I want them to be -1 inch in the z direction. Let me move aside so you can see. That would be vertically down, -1 in the z direction. Okay, say OK to that. And then what we need to do is tell the program what parts might contact what. So before I do that, since this O-ring might contact multiple surfaces of this little pocket, I'm going to select those surfaces and we'll put them into a single group. So selecting the surfaces it might come into contact with, I'm going to right click and I'm going to say create new group. So now if I deselect all that, you can see I have all those in a particular group. So I'll select that group and the outer surface of that O-ring, and then I right click and say you guys might come into surface contact. Okay? And then likewise the outer surface of that ring with the bottom surface of our lid, if that's what you want to call it. Right click, contact, surface contact. So you're always making contact pairs. This might come into contact with this might come into contact with this, but it might be multiple surfaces within that one thing. Okay, from there we're just about ready to analyze. In fact, you could analyze the model at this point. Since this is a mechanical event simulation, it's going to give us steps through the solution so we can see as that top piece is moving, what does that motion look like? How are my displacements changing? My stresses changing? The default number of steps that it gives us, I think, is a little bit coarse. So I'm going to right click on the analysis type, say edit analysis parameters, and we're going to change the number of time steps from 20 to 200 just so we get a better picture of what's going on. We'll say OK, and then from there I can run the simulation And the nice thing about mechanical event simulation with nonlinear analyses, one of the things I like about it, is that as it solves the analysis, you can also move the analysis window to the side, or you can minimize that, and then you can actually watch what's happening during the analysis, so you can make sure that the behavior of the model is what you expected. If you see something peculiar or you see something obviously wrong, you forgot to set some constraints, for instance, on the bottom part here, then this part would start moving away or drifting into space. You can always stop the analysis via the stop button there, go back, make the changes, adjust your load, or adjust your displacement. So there you can see we're beginning the contact between the O-ring and the pocket. It's starting to become a little bit egg-shaped. Obviously in contact with our lid is helping to push it down and inside there. In my analysis window, this gives me a running percentage here, so I can see that we're about almost 80% of the way through the solution there. And about 97% there. All right, so there my analysis has completed. There's my mechanical event simulation. So similar to what we saw before, it will give displacements as your default output. Of course, I'm seeing a maximum displacement of about 1.01 inches. I had forced the displacement on that lid to be an inch using a prescribed displacement. And then you can take a look at stresses in the model. So if I want to review the stresses, I can see that. You can also play an animation of those steps. So there is an animation right there. Not only can you play it, but you can also export it as well. So you can do a file, export animation, to create an AVI file, share with somebody so they can see what's going on in the solution. It's kind of neat. You can see it makes that first impact, comes up, impacts again with the lid. No gravity on in this analysis. Had we had gravity, it would probably come down and sit here and wait. Actually, these guys would, no, this one I was thinking would drop at the same rate, but actually we're prescribing motion on that one. That one would be just free falling in space had we added gravity, but no gravity on this model. But anyway, you could certainly turn it on. What I was going to say was, if you look at the stresses in the model, again, you take a look at the results of your analysis. From there, we could say, I want to make some changes. I could use a different material. My stresses are really low. Maybe it doesn't need to be this thick. We could save some material, use a thinner sheet of material if perhaps you're making that box by breaking it into at two corners to make that box shape that the O-ring fits within, something like that. You can also take a look at and do graphs. So if I do something like a rectangle select nodes, I'm going to select all the nodes here at the top of that lid, and I'm going to change the result that I'm looking at to something like reaction forces in the z direction. And then what I can do is say edit new graph, and there's the sum of all the reaction forces at those nodes. So you can see it starts to come down. There's where it hits the O-ring, and then the O-ring bounces off, it hits it again, and then there's the insertion. So you can get the insertion force or the reaction force required to push that O-ring in. Again, we used a pretty soft material. The force required is pretty small. It's less than 1 pound force in order to do that. But you can certainly output that data. I've seen that actually used in an automotive application where they're looking to see what the insertion pressure was on a seal. And moving on down to our final slide there, one last thing about that model. In our model, even though we had just a planar section, what you're seeing here, you can also turn on 3D visualization. So if we turn on 3D visualization, it adds that 1/2 inch thickness that we defined. You can also make parts transparent, as you see there. I did with a couple. So you can really make some nice presentations. In summary, there is flexibility. So you have multiple paths to take, elements to choose from whenever you're considering simulation on an AutoCAD. So if you thought that the only thing you could do was take lines from AutoCAD to simulation, that's not accurate. You can do multiple different types of elements. Consider simulating existing AutoCAD geometry or leveraging AutoCAD to create geometry for simulation. So you might already have various parts drawn within AutoCAD. Now you can do some simulation on them. Or if you're already a simulation user, you might want to consider using AutoCAD. So you could very quickly make up this sketch in AutoCAD, import that. That's a much simpler model to analyze, that 2D model, than had I actually modeled this in 3D. There's an awful lot less contact with the 2D version. So consider AutoCAD as well whenever you begin a simulation. And then lastly, leverage the simulation software to evaluate the results before you commit to a particular design. So you have a design, run some simulation, see what it looks like, see if you can change, alter, improve that design. Thanks for watching. Have a good day.